I'm a professor in glaciology and climate at the Geological Survey of Denmark and Greenland, and I want to talk about the physical mechanisms behind this tipping point for Greenland. And an important frame is the fact that the Arctic is warming 3 times faster than the rest of the globe. This Arctic amplification, driven of course by stunning spikes in enhanced greenhouse effect. We're at 50% above pre-industrial carbon, and the land ice is having its delayed reaction to this abrupt impulse. This 3D rendering of Greenland presents it as a dome of ice resting on land. And this tipping point that we're talking about involves something called the elevation feedback. And on the left, you see the elevation profile with the ice dynamics moving the ice through the system. You see the colder atmosphere above. And in a thinning scenario, what you end up with the shape of the ice sheet is a much larger area exposed to this higher temperature. And this presents an amplifying feedback as the ice sheet draws down into warmer parts of the atmosphere. This amplifies the warming. This is the tipping point. This is the irreversibility for the ice sheet. The black line illustrates how the area of ice increases non-linearly with elevation. That's what you saw in the previous slide. To reinforce, this is a non-linear mechanism. Greenland is by far the largest land ice contributor to sea level rise. The blue area is the ice sheet itself. There's a red wedge at 6%, meaning that 2/3 of Arctic land ice contributions to sea level come from Greenland. And Arctic ice in the amber curve is much larger than the contribution from Antarctica on the lower curve. But what's more important is that all of these curves have been increasing their sea level contribution in each following decade. That represents an acceleration, which makes it very difficult to project this into the future. And I'm going to talk about why the ice sheet models are essentially unable to give us a high fidelity projection into the future. To familiarize you with the bare ice area, you have water-saturated snow, the blue areas, absorbing more sunlight, and the impurity-rich bare ice, absorbing much more sunlight. The sunlight absorption is by far the largest contributor to melt energy. So this expansion of the bare ice areas is one of the amplifiers, one of many amplifiers that I'll talk about. And this is to illustrate how it takes a long time for the ice to accumulate, but the ice can break away in a matter of minutes. And on an earlier slide, you could see that sea level during the ice ages gradually decreased during the several ice ages because it took millennia for the ice to accumulate on land. Well, the sea level then it rises abruptly as we exit the ice ages because, as you can see here, this 900-meter thick iceberg breaks away in a matter of minutes. So the ice is lost much faster than it is accumulating. And to tell the story, it's useful to use this narrative device, follow the water. It's kind of like in politics, you want to understand what's happening, you follow the money. Well, if you want to understand what's happening on glaciers, you follow the water. And as you saw before, water-saturated surfaces absorb much more sunlight. These are solar collectors. This is 1.5 kilometers wide, 30 million cubic meters solar collector. This factor is not in the climate model projections. All of these lakes essentially drain into the ice at some point during each melt season. So they deliver 0 Celsius water into -10 ice sheet interior through infiltration. And that infiltration means that delivered to the ice internally. And that internal heating produces softer ice because warmer ice can deform more readily. As you can see, the water eventually makes it to the bottom side of the land ice. And that's where it comes out, it rushes out. It entrains sediment, and you can see the muddy water that's right up at the front of the glacier. Because this fresh water is lighter than the salt water, it immediately rushes upward. This effect, like the one before, the melt-induced acceleration is not yet in the ice sheet models used to project future sea level rise. The water that's coming out is extremely turbulent. So this is a forced convection heat exchange, much more efficient than just warm water in contact with the marine terminating ice. This illustration shows how it's typical to have a +4 Celsius Atlantic layer at depth. And this is right at the grounding line where the water comes out at the bed and entrains this warm water and forces a heat exchange right at the front of the ice. So as the ocean warms, delivers more of this strongly melt-inducing warm water. This ensures the connection of a warming ocean with the ice sheet. Yet another factor is hydrofracture, the fact that liquid water is heavier than ice. This water, when filling depressions, it exerts a greater force at the bottom of these cracks, and provided that the rifts here are kept full with water, that ensures that will cut open ice shelves. And this is precisely what happened on the former Arctic's largest ice shelf in northwest Greenland in a record warm summer. The rift here was water flooded, and we had 3 times Manhattan Island area breaking away. 2 years later, another then new record warm summer, we lose large areas of the site. So the hydrofracture mechanism, yet another not included in the models used to project ice sheet contributions to future sea level rise. South Greenland, all around the ice sheet, at the margin, you see this dark ice. You see the stripes. What's causing the darkness? Why the stripes? Under conditions of prolonged sunshine, droughts, which are occasionally happening in longer duration because the weather systems are becoming more stationary as climate unravels, you get really dark surfaces like this, where the surface is absorbing 4 times more sunlight than it would with a pure bare ice surface. And this was an instance where there was 6 weeks of sunshine. And for some reason, the surface got so dark. This is down in the lower parts of the ice sheet. Why was this happening? When you sample this material and look at it under a microscope, it's biological. Microbial darkening. These microbes regulate photosynthesis to do their life cycle, and they produce the darkness. The dust particles, you can see they're translucent. This is quartz, but it contains nutrients that the microbes need. This is yet another factor not in the climate model projections for sea level rise from ice sheets. It's a climate X factor because we still don't know if pollution is fertilizing them, and we don't know how high on the ice sheet they will colonize. We do have reconstructions of the ice sheet. This one's very interesting, more than 100 years long, and you can see the recent accelerating loss of ice. And then in between the 1960s and 80s, the ice sheet was stable. There's sufficient evidence to convince me that was due to sulfate cooling, so-called global dimming. This was from the burning of coal in the atmosphere, and as we transition off of coal into cleaner coal and less coal, we have an aerosol unmasking, and that will enhance the melting on Greenland. The removal of the aerosol masking effect is one of the very alarming aspects of having cleaner energy. Here's a river system that shows that the temperature on the coast produces a nonlinear increase in runoff through this river system. It's actually to the third power, so it's an extremely nonlinear sensitivity. So that's one of the main messages here is these nonlinearities make it very difficult for us to conceive in our minds just how responsive, how sensitive, how quickly the ice can go. Another measurement-based study finds a similar conclusion where there's, again, a sharp increase in melting based on temperature. This means, of course, that as Arctic continues warming faster than forecast, that we can expect a very sensitive response of Greenland ice. We had a stable period of sea level, 6,000 years, under which civilization developed. And what we face in the future is somewhere in between those two curves. The lower constant 1990 emissions is behind us in the rearview mirror. The business as usual scenario, it seems unlikely. We may essentially crash the climate before we can even possibly burn all of that fossil fuel. So the truth is somewhere in between. But as you can see, the expected sea rise in the coming centuries is absolute catastrophe. Can we slow this down? I think that's what hopefully the leadership at a meeting like this can get this kind of a message and get busy with the monumental, enormous task of not only reducing carbon emissions, but somehow removing gigatons of carbon from the atmosphere. The era of abrupt sea level rise is upon us. I'm sure that we face other more immediate challenges through the loss of water and food security. At the moment, we're not running for the hills, but it's time to start walking. And to kind of try to sum up, the Arctic climate was actually cooling. We were heading for another ice age, but due to industrial output, we entered an era, the Anthropocene, where we shoot out of what should have been the next ice age, which would have been very difficult, but we've gone far off into the unknown. And the projections of the future, brace yourselves, they're like this. The Paris scenario is the lower curve, and the business as usual is the upper curve. This is what negotiators here need to make sense of. What is at risk is basically a governable society. Thanks for your attention.
Thank you very much for this very nice presentation. And so there is time for some questions from the audience here. Yeah, please. Is this working? Yeah.
With the, not working. Is it working? I don't know, it's not working. Okay. Yes, so a question about the melt rates of Greenland, what you would expect, how much you would expect them to increase when we lose the Arctic sea ice. Say we lose the Arctic sea ice in 5 years for a month, and then a few years after that it's gone for 3 months or 4 months of the year. How much will the rate of melt on Greenland increase as a result of that loss of sea ice?
Yeah, in the last 50 years, Greenland melt has doubled. And as we lose the ice in the north, there's already evidence that the largest warming around Greenland in the last 50 years is in the north. And it's the reason why the Arctic is warming 3 times faster than the globe. It's the loss of Arctic sea ice. So we're already seeing increases in melt in the north. And as the sea ice retreats across North Greenland, we will see the most warming there. And presumably, predictably, that those now kind of ancient, steady, non-accelerated glaciers, those two will accelerate, and one of them is the largest ice stream that has some underwater bed that goes into the deepest parts of the ice sheet.
Many more questions? Yeah, please.
Thank you very much. That was absolutely fascinating. In terms of some of the water issues that you raised and that you said are not fully accounted for in the models, is that a question of more observation and more science, better models, better computing power, and are there any projects in place to improve those models at the moment? Thank you.
The modeling community has been making big advances. However, due to coarse resolution in the global climate models, it to some degree, it's not even the fault of the ice sheet models. It's the fact that the ocean projections lack the resolution to resolve the narrow ribbons of warm water that get into the fjords. And the atmospheric models don't yet resolve these highly amplified waves that produce extremes like the record warm Pacific Northwest heat wave, for example. So that's just the problems in the atmospheric models. Then the ice sheet models, they struggle with the iceberg calving physics. They're like the atmospheric models. The ice sheet models are full of so-called parameterizations, which are facsimiles, approximations, kind of computer time shortcuts that are necessary because the models are being run kind of state of the art, but they're just unfit for the task at the moment, which is why the discussion remains about the so-called long tail of ice sheet decline. There is a low probability yet high impact possibility that's still very much plausible, and my opinion is that the chances of extreme sea level rises are something that should be taken extremely seriously because it's very much in the cards.
I also invite people from Geneva and Stockholm that are following us to type the questions in the chat box, if any. Otherwise, okay, one more question, please.
I got the impression towards the end that you were at least perhaps hinting at, even if we stopped our emissions of carbon dioxide, let's imagine by 2040, 2050, that the level of CO2 in the atmosphere and the level of warming we actually got would actually lock in significant ongoing sea level rise for some significant time to come. So are you really saying that if we are serious about stopping some of the worst impacts of climate change, we are going to have to remove absolutely huge quantities of carbon dioxide from the atmosphere? Mitigation simply is not enough.
Yeah, and I might go further that because the oceans have been absorbing so much of the heat imbalance of the planet, even were we successful in removing hundreds of gigatons of carbon in the atmosphere, we would still be looking at a destabilized Antarctic ice sheet. And as you saw from the shocking kind of boomerang-shaped curve, even in the Paris scenario, Greenland will remain beyond its threshold of viability. So it's a matter of time until the elevation feedback, the drawdown, this tipping point of Greenland becomes irreversible. The good news is any brakes that get applied now will slow that process down, buying time and saving lives.
Okay, so thank you very much.